I'm going to do this problem from the homework. It always confuses people. I do it every year and it confuses me too. So let's just read through the problem here. So what you're looking at is the relationship between the length of a password and cryptographic security. So this is a very important thing to understand. So we have an assumption here to begin with, which is that we're looking at a password which is 10 characters long. And we're going to assume that each one of those 10 characters could be one of 128 possibilities. Okay? All right, so it says, what is the size of the key space that consists of passwords of this form? So what it's asking is, how many passwords are there that are 10 characters long and are one of these 128 characters? So maybe it's clear. So where do I have the right answer here? It's 2 to the 70th power. Where does that come from? That comes from, let me see if I can zoom in a bit here and also draw. Can I draw here? So we have 10 passwords. That means there are 10 blanks here. I'm just going to put ... because, and so what we mean to suggest is that there are 10. And for each one of these blanks, there are 2 to the 7 things that could go there. So 2 to the 7 times 2 to the 7 times 2 to the 7. So these are all the possibilities. And if you multiply all these 2 to the 7s times each other, what you get is 2 to the 7 to the 10th power, because there are 10 blanks, which is 2 to the 70. So your answer will not be 2 to the 70 because these, well, possibly it will be, but these numbers are randomized for every student. So you're going to be dealing with different constants, but the reasoning is going to be the same. So it says, what is the equivalent key length in bits? So if there are 2 to the 70 possibilities, the number of bits it takes to represent all of those possibilities is log base 2 of the number. So log base 2 of 2 to the 70 is 70. All right, so this is 70 bits of security. And just as an aside, we know that that's less than the 128 bits of security that we usually require in cryptography. But if the adversary has to check all of these in an online fashion over a network, then that might be acceptable. Assuming that you could check one password every millionth of a second, what is the worst case running time for cracking this password by brute force search in days? And so here's the answer. So how do you get this? So you have, where's my little sketch pad here? So we have 2 to the 70 passwords that we have to check. Okay, and we're checking them at a rate of 10 to the minus 6 passwords per second. Wait, is that right? No. That's 10 to the minus 6 seconds per password. Okay. All right, so if we multiply these two numbers, look at the units here. The units of this number is passwords. The units here is seconds per password. So if I were to multiply those, 2 to the 70 times 10 to the minus 6, the password units would cancel, and this would be something seconds. Okay, and so the important thing is that the units here is seconds. Okay, and now I just have the problem of converting this many seconds into days. So if I divide by 60, there's 60 seconds in a minute, so this becomes minutes. Okay, and then if I divide that by 60 again, there's 60 minutes in an hour, so the units here becomes hours. And if I divide this whole thing by 24, there are 24 hours in a day. So now finally the units are days, and this is the right answer. So you have to use a calculator to do this. There's one way. Let's see if I can get this going. Terminal. One thing you can do is use Python for a calculator because it can handle really big numbers. Let me see if I can get this going here. So I can do 2 to the 70. And then what am I doing? I'm dividing that by 1,000,000. and then I'm dividing the result by by 60, then by 60 again, then by 24, and I'm getting this number. And then I can copy that number and put it in here, and that's where I get that answer. So here's the next part. Now assume that the user only used 27 characters from the keyboard. What is the key length in bits in this case? So let's go back to the sketchpad and think about this situation. So now we have 10 blanks just like before. We have a 10 character password, ... But now there's 27 possibilities in each position here. So the total number of passwords that are possible with, if there are 27 characters, such as like the lowercase alphabet plus space or something, let's say, then there are 27 to the 10th possibilities. And if you want to know how many bits it takes to represent that, that is log base 2 of 27 to the 10th power. Okay. All right, so you can go to your terminal here and you can figure out what that number is. One way to do that is to import math and do math.log of 27 to the 10th power base 2, and I get 47. Now the number of bits has to be an integer, so I round that up to 48. And that's where this 48 comes from. Now it says how many days in the worst case would it take to break this weaker password? And the reasoning here is the same as what we did before. So we have 27 possible letters and a password that's 10 characters long. So this is the number of passwords. So again, we would divide this by 1 million. And what would that be? That would be the number of passwords we can check per second. And then if we divide this by 60, it's the number of passwords we can check per minute. And if I divide this by 60, it's the number of passwords we can check per hour. And then if I divide the result by 24, that gives me the number of days it takes to check all those passwords. So coming back here, you get this number. And let's just think about this, right? So here, 70 bits of security. We know that 70 bits of security is not really safe, but this is still a lot of days, right? And this is much, much less. So this would be very insecure. This is why those password requirements always tell you to use uppercase characters and symbols and stuff like that. It's because if you just use lowercase letters, they're just, there are too few 10-character passwords. So supposing you only use 27 characters, how long is the shortest password that achieves 204 bits of security? So let's go back to the drawing board here. And what do we want? We have 27, but now we haven't decided how long the password is going to be. It's going to be X characters. So now we have a password, and in each blank, one of 27 characters is going to go there. And the password itself is going to be X characters long. We're going to make it as long as we need it to be in order to get 204 bits of security. So the bits of security is going to be log base 2 of however many passwords there are. And I want this to be equal to 204. So now I just do some algebra. Can I get an eraser? I want some space. So, you know, one of the nice properties of the logarithm function is that it spits out exponents, and so this is the same thing as x times log base 2 of 27, and so x is equal to 204 divided by log base 2 of 27. And again, I can do that in my Python calculator here. I can do math.log of, sorry, I'm going to 204 is in the numerator. 204 divided by math.log of 27 base 2 turns out to be 42.9, but if we're talking about bits, it needs to be an integer, so we round it up to get 43, and that's where this 43 comes from, and that's how you do